Hello and welcome to Fabricam's presentation. This video will detail the internal design considerations that will need to be made for the setup of the plant, in the form of a brief simulation process description, the reasoning and justification behind the model chosen, and energy analysis in the form of the pinch method and a summary of the results obtained.
At the beginning of the process, ethylene and oxygen gas are compressed at 20 bar. Ethylene passes through a normal heater operating at 270 degrees Celsius, whereas oxygen passes through a heat exchanger with an exchanger duty of 169,244 calories per second. Some of the heat will be transferred to the second last distillation column towards the end of the process, and the excess heat from this distillation column will be recycled back to heater via a splitter to further heat the oxygen. After passing through the mixer, oxygen and ethylene oxide undergo an oxidation reaction at 270 degrees Celsius and 20 bar. Then the mixture flows through a cooler to prevent a thermal runaway from occurring, since this reaction is highly exothermic. This cooler is operating at a temperature of 30 degrees Celsius. Then the ethylene oxide produced flows through an adsorption column with water flowing from stream 8. The top distillate contains byproducts that cannot be removed, such as ethylene glycol and any ethylene oxide that has not been adsorbed. The adsorbed ethylene oxide passes through a desorption column to remove the water and is further purified via the refinery column over here. Fabricam have decided to remove 60% of the ethylene oxide at this point to sell. The remaining ethylene oxide and ammonia reacts at 80 degrees Celsius and 12 bar, and this reaction also contains water that's flowing from stream 22. The unreacted ethylene oxide and ammonia is recycled back into the reactor via the top half of the flash drum and from stream 26. This is done to increase the overall conversion. Another desorption column is put in place to remove water, which flows through the distillate, and a solution containing the precursors ethanolamine, diethanolamine, and triethanolamine pass through the bottom stream. Ethanolamine is the most plentiful out of the precursors and has the lowest boiling point, so it is removed first. Then the remaining two precursors, diethanolamine and triethanolamine, are separated over here.
Energy consumption. From the stream tables provided from the base case, the areas that consume or generate significant amount of energy were identified. In order to maximize the use of energy, a pinch method was applied to these hot and cold streams. There were 6 hot streams and 8 cold streams in total. The cascade diagram allowed the pinch point to be calculated in the interval 181.5 degrees Celsius to 191.5 degrees Celsius. After sketching the network design for above and below the pinch, possible heat integration were identified. These were: for above the pinch, heat exchanger goes from heater to distillation column, as shown here. And here the total energy is 700,667 calories. For below the pinch, there were 4 possible outcomes. These were: heat exchanger goes from heater to refinery column, heat exchanger goes from desorption column to distillation column, heat exchanger goes from refinery column to distillation column, and heat exchanger goes from distillation column to another distillation column, as shown here. And the total energy here are 4,961,277 calories, 110,429 calories, 8,234,578 calories, and 17,285,079 calories, respectively. However, during the actual simulations, the only feasible option for below the pinch was heat integration from heater to refinery column.
So, thermodynamic modeling in our span simulation, we choose to use NRTL and RK equation. This is because in binary system we can use Unifact, Wilson, elect NRTL, and some other equations. But Unifact is has a large deviation in the estimation of the vapor phase small fraction of the alcohol containing system. The Wilson modeling is more accurate for complete miscible system, but its calculation accuracy for partial miscible system is poor. The elect NRTL focused on the interaction between ions, which is more suitable for the fully ionized ions in the liquid phase. The NRTL equation can be used to obtain the binary data of multivariate vapor-liquid equilibrium and solution equilibrium. And its activity factor can be better to correlate and predict the relationship between the gas-liquid equilibrium of the binary system and the infinite dilute activity factor of the organic component with temperature. Especially for the parameter prediction of the miscible system and water containing system, it is more accurate than other equations. And in gas estimation, we have a PB equation, which is more suitable for estimate the interaction force between petroleum gas and molecules in the petroleum system. The ideal model, which is most suitable for the ideal gas system, PSRK equation, which is suitable for the polar or non-polar light component gas component system at a higher temperature and pressure, and the RK equation, which can approximately describe the real gas behavior, especially for the hydrocarbon and other non-polar gas prediction actually, and the applicable temperature and pressure range is wide. It is suitable for the description of fluid property above the gas liquid critical temperature, and also has a more reasonable description for liquid and low pressure gas whose temperature is slightly lower than the critical temperature.
To summarize, our final case simulation ran without errors, and there were no convergence errors, and a stream table can be produced.
In this video, Fabricam offered and presented the simulation decisions made for the setup of the Aspen program, provided a full justification for the model chosen, NRTL-RK, from the energy analysis of the pinch method, provided heat integration options for the setup of the plant, and summarized all the results that were obtained. Thank you for listening.